Okay, I think we can get started now. So I want to begin by saying a very, very warm welcome to all of you who are joining today's HBCP webinar. And I'm sure that some of you, many of you probably came last week to the very first one in the series. This second one is part two of a general overview of the Human Behaviour Change project. I'm very glad to be able to welcome Jana Hastings, who's here in person, who I will introduce herself in just a minute. But before that, let me just introduce myself and also our absent friend, James Thomas, who can't be with us today because it is in fact a UCU strike day here in the UK, and I'll just say a little bit more about that in a minute. But myself, I'm Robert West, and I'm Professor Emeritus of Health Psychology at University College London. And I've been working in the field of behaviour change, and specifically addiction, and even more specifically, smoking cessation, as well as some other areas for many decades now, and I'm a part of the Human Behaviour Change project as a behavioural scientist. James Thomas is a systems architect and a data scientist who also works at University College London and has been leading a lot of the technical work, particularly in relation to part of what we're going to be talking about today, which is the automated system for gathering relevant papers from the scientific literature. And then let me introduce or allow Jana to introduce herself very briefly.
So thank you, Robert. So hello, everybody. I'm really pleased to be here. I'm Assistant Professor of Medical Knowledge and Decision Support at the University of Zurich in Switzerland, and also with the University of St. Gallen in Switzerland. And my background is I'm originally a computer scientist, and afterwards I've done some work in computational biology, and for many years worked on ontologies and algorithms that use ontologies. So really excited to have been a part of the Human Behaviour Change project and talk a little bit more today about some of this work.
Thanks very much, Jana. So yeah, just to say a little bit about the UCU strikes, particularly for those of you who are not in the UK. Some of you may have noticed abroad, as we have noticed in the UK, that we have a particular kind of government that is very rare in UK history, which is in terms of its behaviour. And there's been a lot of strikes, and there continues to be a lot of strikes in the UK as a result of policies of the government, particularly in relation to public sector paying conditions, where public sector workers have seen successive reductions effectively in their pay and worsening of conditions. And eventually something has to give, and UCU has decided, in my opinion, absolutely rightly, that the only way forward here is to take strike action, which no one takes, particularly given the loss of pay and so on, lightly. It's absolutely a last resort, but things have got to a pretty bad state. Now we're doing this webinar on a strike day. I'm actually retired, and so not paid by the university, and just do everything for nothing anyway, which is almost like what academics seem to be doing these days. But we felt that it was really important, notwithstanding this, that we go ahead with this webinar, particularly given the large international audience. So my absolute solidarity with those who are on strike, and I do hope that any of you who are in the UK who are affected by this will support the action that's being taken. Thank you. Okay, so the agenda today is that we're going to run a 25-minute film with James, Thomas and Jana talking about the technical and computer science part of the Human Behaviour Change project. And then we're going to spend the rest of the time, which will be about 25 minutes, discussing it. And it's open to questions and so on. So the discussion format goes like this, that there's a Q&A box, which if you move your cursor down to the bottom of the screen, it should show up as Q&A. Post any questions you like as we go through the film. Ideally, as soon as they occur to you as the film is going on, in the Q&A box, and then monitor that if you will, and what's known as upvoting any questions that you want answered, because what we'll do, because there's likely to be more questions to answer than we can answer in the session, what we'll do is we've on our screens we'll see the ones that have got the most votes, and we'll answer those first. I mean, maybe we'll get to all of them, I hope we do, but it just makes sure that we at least get to the most popular ones. So so do that. It's the question and answer thing, not the chat. However, we also have a chat facility for you to talk to each other and just generally make observations and network and so on. And we will also keep a record of that. So we'll keep a record of all the questions asked, and we'll share these on the Open Science Framework, and there's a link to that at the end. The recording is being, the webinar is being recorded. The last one was recorded. They're all going to be recorded, and they will be uploaded onto YouTube, and there'll be links on Open Science Framework to those recordings and also to the slides, because sometimes with recordings, it's not always that easy to read slides if there's small writing. So all the slides will also be available for you. So we want to make everything available as much as possible. Right, okay, I think that's it. So don't forget to put your questions in the Q&A as you go along. Now we're going to just play the 25-minute video where James and Jana are going to talk about the technical aspects of the HBCP. So here goes. It'll take a couple of seconds.
Well, good morning, good evening, good afternoon, depending on where you are, and welcome to this latest webinar from the Human Behaviour Change Project. My name is James Thomas, and I'm based at UCL in London. And myself and Jana Hastings will be taking you through a webinar on the second part of what is the Human Behaviour Change Project. And we're going to be taking you through some of the technical details of what we've been doing in this project. So first of all, I'll take you through some of the overriding objectives for what the Human Behaviour Change Project is doing, why we need evidence surveillance, and some of the challenges we found in extracting information from published papers. And then Jana will take us through ontologies, why they're useful for prediction, and then a specific use case around smoking cessation from an ontology annotated during the project. So first of all, I'll take you through evidence surveillance and information extraction, the contribution of the systems architecture part of the project. And this really stems from an overriding problem that we've got in our research environment. The first bullet point here summarizes it. Globally, we systematically lose research every day, and then either we don't use it or we spend ages finding it again. And what I mean by that is that a lot of research is published every day. A lot of research is conducted, but we don't really have good systems for keeping track of what happens to it once it's completed, once it's published. We have these huge databases where millions of publications are stored, and then if you actually want to find out what we know about any subject, we can end up spending months, sometimes years even, conducting systematic reviews of the evidence base to find out actually what we already know about a subject, but it takes us a very long time to actually find out what it is. So the first aim of this project has been to overcome some of those problems and set up an evidence surveillance system. So in our area, we've been focused on behaviour change, but also smoking cessation in this part of the project. We've set up an evidence surveillance system, and the idea is there to keep track of research as soon as this is published, to identify it and put it in our own data store. Of course, once we've then got the information in the data store, we need to know what it is and what we can do with it. And then in other parts of the project, we then want to make predictions based upon it. So we then need to extract information from the published papers. And so that's part of what I'll be talking about now as well. So the evidence surveillance workflow. It's a slightly complicated slide, so I'll talk you through it step by step. So over on the left-hand side here, we've got the OpenAlex data set, which is what we're using at the moment, which is currently the world's largest open access database of research publications. There's well over 200 million records in there now, and it's being added and it's growing all the time. So every day, actually, the data set increases in size. We've been looking at it every couple of weeks or so, but we might change the frequency that we're downloading new papers. But essentially, we can almost now keep a day-by-day account and a surveillance of the research as it is published in that data set. And as we've got on the slide there, around 800,000 it seems arrive every couple of weeks, sometimes more, sometimes less, but that's an awful lot of research to keep on top of. So what we've been doing is we've been using machine learning to help us to identify the literature that we're most particularly interested in. So we've integrated this into our EpiReviewer systematic review software, though it's also sort of sitting there slightly separate so that we can integrate it into other platforms too. But essentially, the units that we're working with is what you might think of as a review or a database or a collection of papers. So on the right-hand side here, we've got a review on COVID-19 evidence surveillance. We've got a review now on physical activity, which was the second topic that we've looked at in the Human Behaviour Change project, and a review on smoking cessation. And we've got lots of other reviews. There are about 60 to 70 reviews now currently in the system, which are now using this evidence surveillance technique. So what we do is every single review in the system is uploaded into a machine learning environment where we build a machine learning model for each review, which basically looks at the papers which are already included in the review, and then using fairly standard machine learning approaches, builds a model so it can predict when a new paper comes in whether or not it's likely to be relevant. So when the new papers arrive, every single review is scored. Every single paper is scored against every single review, and those that are close in terms of their distance from the new papers, those papers are then automatically added to the new reviews. So, for example, we've been doing that on COVID-19 and now on long COVID. For the Human Behaviour Change project, those that are relevant to the Human Behaviour Change project domains, physical activity and smoking cessation, we then go through another stage of machine learning where we look at the domain-specific issues. We're interested in randomized trials there, so it goes through a randomized trials classification, again using machine learning, and then we identify those papers which look relevant for the Human Behaviour Change project, and they get posted in those databases. And we run this every 2 weeks to every month, depending on how many papers have arrived and when we've received the latest a new update. What we're expecting to do, though, is to increase the frequency of updates, because OpenAlex is now releasing updates much more frequently than it was before, and also its precursor, Microsoft Academic, tended to do either a 2-week or a monthly cycle of updates. So an example of how we're using it and how we have been using it throughout the pandemic is we've got the OpenAlex data set again here on the left, going through a machine learning model, deciding whether or not a given record has been about COVID-19 or not. Those that are about COVID-19 then go through another machine learning model. This is based on a BERT technology, and that then assigns it to these broad categories, which then go into the live database. In situations where the robot, the machine, wasn't able to tell, then human judgment was there to make those fine-grained decisions when the machine was unsure. We've actually found now, though, that we've got so much information on COVID-19 that actually this whole process can be fully automated. So we've gone from a position where at the beginning of the pandemic, we didn't really expect quite so much research to be published, where we had a completely manual workflow, to one now where we've changed the source. We're not using Embase and PubMed in the traditional systematic review sources, because OpenAlex has basically got everything that we need. But then we're all doing all of the study identification and the classification all automatically, which has been saving, if we had been doing it manual all the way through, though we probably wouldn't have had the resource or the money, would have saved tens to, actually, I think we might even be into the hundreds of thousands of pounds now in terms of curating that data set. So I'll move now on to information extraction. So assume now that we've identified the papers as they've been published, they're in the system, and what we want to do is to be able to identify specific behavior change techniques and specific characteristics of study populations, etc., and also obviously the findings of the research. And there are different approaches to doing this in an automated way. We can use an unsupervised approach, where a domain specialist generates a search query, semi-supervised, where it's been inferred from the training data, and supervised, where machine learning has been employed. And the first part of the Human Behavior Change project with the computer science team used a lot of supervised approaches, and you can see on the right there the types of attributes that were being identified from the research reports on behavior change, and then also the performance of that system. What we found very difficult, though, this stage of the project is identifying the arm structure of a clinical trial or a randomized trial. When you're evaluating a particular intervention, what you usually do is you randomize people to receive the intervention and people to either receive a different intervention or no intervention at all. And whilst that is fairly clear, that structure, when you're reading a research report as a human, it's actually very, very difficult for a machine to be able to pick the structure of a study up. And so associating behavior change techniques and outcomes, etc., to specific study arms proved intractable. And that meant, of course, then that if we want to use that information for prediction, it was very, very difficult to do so because we didn't actually have the structure of the trials represented in the automatically structured data. So what we're now doing is a new approach where we're sort of using more of the structure of the paper to give us some clues about the structure of the trial. There is something called the consort statement, which is a reporting guideline for randomized trials, and that's what we're using as the basis of this new information extraction process. We're using the fact that according to the consort statement, you're expected to provide a graphic, a flow diagram, which depicts the structure of your study. And we also know that results are usually presented in tables. They're not usually presented in text. And again, that's something of a challenge. If you feed a PDF file, which most of these trials are reported in, if you feed that into an automated system, you can extract all the text, but often you lose the structure of the table. And it's really important if you're wanting to read a table, obviously, to know where the rows and where the columns are. So that's one of the focuses that we're looking at now. So first of all, we're taking the structured data from consort flow diagrams and identifying the arm structure that way. And then the next stage, we're nearly there actually at this now, is to link those data to data that we find in tables. So just walking you through the information extraction from consort flow diagrams, we're starting with a standard consort flow diagram. You can see here, the usual structure here, the number of people assessed for eligibility at the top, number of people excluded for different reasons, the number randomized, and then you randomize into two arms, how many are lost to follow-up, how many are in the analysis, etc. That's a fairly standard structure for these diagrams. And you can see it starts at the top with most of the boxes in the middle and then splits. And it splits into two or more arms, depending on how many different interventions are being evaluated and tested against one another. So we start with that. And what we do is we use image recognition technology to identify the boxes. So this is an example of an early effort to find the boxes. And you can see that what we've identified here, we've put sort of green lines around the boxes that have been identified. Some of them have been identified well. You can see there have been other boxes which have been identified for some reason, best probably known to the algorithm, and this box here hasn't been completely recognized. So we've been doing quite a lot of work to make sure that we can identify some of those problems and sort them out. And we've actually now got a really good algorithm for identifying the box structure in these consort flow diagrams. What we then got, of course, is if we can draw lines around the boxes, we can know where the coordinates of the boxes are. So you can imagine we've got XY coordinates for every single box. We know how many boxes there are, and we know where they are and how big they are. What we then do is we extract, we sort of, if you like, copy and paste each box separately. So we're able then to take the image and snip out each box, And what we do then is we send that box, the text in that box, to optical character recognition software, which then turns what is a graphic, whilst we can read the text here ourselves, computer can't until it's been turned back into normal text. And what that then gives us is the box, the position of the box, and the text in the box. And so what we're then able to do is to recreate the structure of the trial in computer readable form in the order and the structure of the consort flow diagram with the text in the boxes. So the next stage on from this is then to link that up with the data from the tables. So just to summarize what I've talked you through there, what we have achieved so far in the systems architecture part of this project is the successful development and deployment of this system for keeping on top of new research as soon as it's published. And we've also found that that's not just been useful in this project, but it's already being useful and rolled out in many other projects that we're involved in and other partners are involved in. So that's been a really useful output from this project already. We're using open data in that, OpenAlex, which makes it much easier to ingest and reuse the data. And we're using supervised machine learning to identify the relevant research and associate it with the appropriate review. This system's contributed to evidence surveillance during the pandemic. And then what we've moved on to now is this, what we think of as a promising new approach to extracting data from reports of clinical trials. I've not actually seen other efforts to extract information from the consort flow diagram, and that does seem to be actually quite a good way of getting the core elements of a trial out of a paper without having to sort of try and encourage or teach a machine learning model to read the entirety of a research report. What we found and what we found as challenges is that we've needed to use cloud computing and parallelization to scale, so processes running in parallel to one another, because obviously if we're running through 800,000, the last update was over 1 million records, 1.3 million I think it was. That's an awful lot of records to run through machine learning models. And if you want it to output the results in good time, then you need to run things in parallel. It's also worth noting that we started with Microsoft Academic and are now with OpenAlex. Open access resources can be fragile, and that's one of the things that we need to bear in mind when we're building and working with these types of systems. And that meant that, as well as that there was inherent vulnerability in that we actually had to do quite a lot of work to move from one source to another. So far, we're really happy with OpenAlex. It's doing a great job, and we're finding that it's been very easy to integrate into this new system. So that's it from me now, and I'm going to hand over to Jana, who's going to talk you through the computer science, the prediction part of things.
Thank you, James. So, hi everyone, this is Jana Hastings, and I'm going to tell you a little bit about the computer science contribution to the Human Behavior Change project in the form of prediction systems. So I will say a little bit about what ontologies are and how we've used them for prediction, and I will describe a system which is able to predict smoking cessation from an ontology annotated data set as part of the project. So why are we interested in predicting the outcomes of interventions? The basic idea here is that by training a model, a computational model, to predict outcomes of hypothetical behavior change interventions, so that might be interventions that haven't necessarily been done, but are similar to interventions that have been done and that we have evidence for. Doing this is a way to turn evidence into knowledge, to turn evidence, the evidence that we have, into something usable for informing decisions about what we do in the future. So predicting outcomes is an objective of the Human Behavior Change project, and an initial part of the work aimed to try and use language models for making predictions. So sort of taking the text of intervention studies and synthesizing that text into a predictive model using a language-based approach. However, the language-based approach failed to capture some of the important distinctions in the domain. such as the distinction between pharmacological and non-pharmacological interventions. And intuitively, it's clear that this sort of language-based description puts words like pharmacological and non-pharmacological quite close together, and indeed they may be talked about similarly in the sense that they're both grouping terms for interventions, but the outcomes are very different. They're very different types of interventions, and they work very differently. They have different mechanisms of action and so on. So some domain knowledge is needed in order to make sense of the literature over and above the words that are used in describing interventions and how those words appear in language. So what we aim to do is to take the domain knowledge and put it into the prediction system through first capturing an ontology to capture relationships between entities. So an ontology is a type of computable representation of domain knowledge, of entities that may be investigated in a domain, together with their hierarchy and their relationships, which might be non-hierarchical, and their meanings in the form of definitions. So each thing that goes in an ontology gets clearly defined, gets related to all the other things, and the whole structure represents some part of domain knowledge in a way that computers can also understand. So these are really useful for a lot of different purposes. They serve as indexes and help with searching, they help with integration, they help with translation from one perspective to another. And in our case, we wanted to use an ontology for representing behavior change interventions to also support and inform a prediction model. So what this means in practice is that the ontology, and here in the middle you see a subset of the ontology for mode of delivery, needs to be associated with the literature, and then those categories that are represented in the ontology can be used as a basis for summarizing the literature and indeed for building predictive models. So the associations between the ontology and the literature, the studies that we're aiming to synthesize, they can be made manually or automatically. For the current stage of where the Human Behavior Change project is at and the current prediction system that we're working with, the associations were made manually and cross-checked between different people. We also explored systems which were able to make the annotations automatically, and these don't quite work well enough yet to be used on a very large scale, but as we develop the system and train the machine learning models, we can expect that those parts will get working better as well. So what this looks like in practice is that you have an ontology which tells you the relationships between entities and what the different entities mean, and then you have some data which is coming from the studies, and this data is associated with ontology terms. And this combination of ontology and data that comes out of the literature is then fed into a machine learning model and used to make predictions. And this is a way of synthesizing the evidence that is in the studies and translating it into actionable insights. So what's key for the prediction system to be usable for actionable insights is that the prediction system be interpretable. And what that means is that you can see the insides of the working of the model. You can see why it made the predictions that it made. So it's no good having a completely obscure and uninterpretable model, because then it might give you predictions, but you have no idea how they relate to the underlying evidence. So we aim to build an interpretable model from which you could see what the predictions were based on. And as the basis for this interpretable model, we used a kind of old technology which is called a rules-based system. So rules are statements of the form if something, then something else. And this type of statement represented in logical form is naturally interpretable. It's sort of close to how humans think about reasoning in practice. But on the other hand, the historical rules-based systems had some concerns. So, for example, you have a need to have a small number of rules and that the rules be short. So you should not, because as soon as you have a very large number of rules and a system of rules which is very complex, you can no longer understand it, even though it's in principle transparent. And you need to be able to learn the rule system from data, but that may mean that you have to transform your continuous input variables into some form that can be translated into a binary true or false statement. And then rules obviously have the opportunity that they can be easily integrated with meaningful categories, such as come from the ontologies. But there was a gap that most rule systems were not implemented using the same kind of efficient machine learning technology that we have today, thanks to innovations in machine learning. So what we did was we developed a system, and I won't go into this technical slide here, but just to illustrate, we developed a system which combined the efficient learning techniques from modern machine learning approaches with a rules-based system that also took constraints from the ontology. And what this means is that we have a system which is able to learn rules from data, so from the evidence data that's been extracted from the literature, and learn those rules in a way that is easy to interpret, but efficient at the same time. So here's the performance of our system as compared to a few other types of machine learning model on the same system, on the same data, sorry. So what we see is a so-called deep neural network system has very good performance on this task. And here the plot is showing you the mean absolute error. That's a way of telling how well a prediction system is doing. We see different approaches such as linear regression and the original approach to prediction, which was based on natural language processing from the text of the evidence. And we see that those other approaches don't do as well. And even another interpretable approach called decision trees does quite badly on this particular problem. So in summary, we found that this novel approach had quite good performance and comparable to uninterpretable models using the same efficient training method, and better than other interpretable approaches. Importantly, the rules that come out of the system are relatively short, and part of what the system is doing is trying to minimize the length of the rules, trying to minimize the complexity of the overall rule system. And it's using the information that it gets out of the ontology, so the classification of different features, in order to do that. So it's one of the things that it tries to do is insist or force the system to respect the arrangement of terms coming from the ontology, and not to have entities that in the same rule that cross different hierarchical levels of the ontology together, because that wouldn't make sense for a prediction, for an explanation. So we are at the moment working on the user interface, which allows everybody to use this prediction system. And we will be shortly releasing a user study of this interface and the rules. What this system does is it has some baseline features which are you can set for both your intervention and your control condition, hypothetically, and then you select one or more intervention component, and you can look at the difference in predicted outcomes. And the rules that were associated, so the sort of reasons why those outcomes were predicted differently in your intervention condition compared to your control condition. So in summary, we developed a novel approach to prediction that was interpretable and used information from the evidence directly as data and from ontologies as a kind of organizing semantic structure. All of this information is available open source, findable, accessible, interoperable, reusable. and we co-developed it together with extensive stakeholder involvement. So thank you very much, and I look forward to the discussion, and here are some links.
Great. Well, thanks, Jana, and thanks, James, for that. And now we're going to throw it open to questions. And I see we've got quite a few actually really good questions already. And we will get through them as quickly as we can. But do keep the questions coming, because even if we can't answer them today, we will get to them, I promise you. And so we'll come back to you. So even if your question doesn't get answered in the session, then do please ask it, and I promise you we will get to. Okay, so the first one that we want to cover is this one here, and just for the sake of making things as quick and easy as possible, I'm just going to read them, but thank you all very much for sending them in. So the first one's from Nancy El Shayeb, who says, the role of the researcher is being transformed. Can this be replicated in a non-clinical trial repository, i.e., for example, qualitative research and qualitative SR? Great question, and I'm going to ask Jana what she thinks, and then I'm going to tell you what I think.
So our current, so I think one question is, can we do this right now? And another question is, can it be done in the future? And the answer to can we do this right now, I think the current sort of model that we have is focused on clinical trials, because that was the initial target that we developed the HPCP for. But I think there's no reason why we cannot adapt this in the future to encompass also qualitative research. The question then is, what does integration mean? Because I think you look for sort of common themes and integrate across different themes. But our current system integrates kind of quantitatively. So this is a really, really good potential future direction, and I will hand over to Robert to give a more definitive answer on this topic.
Or less definitive. So I think, yeah, so the easy part in the future is going to be able to go from RCTs to other quantitative research where you've got a number representing the outcome, because that's what the system predicts. Now, when it comes to qualitative research, and I've had this question before, and I think it's a really good one. You've got to think, well, what is qualitative research doing? What's its role in the whole process? And very often it's not, by definition, it's not to predict a number, but what it is to give you that rich understanding of what numbers mean, or understanding of things that you can't represent in numbers, because you have to think of it in linguistic terms, for example. And there, I think I can see stage 2 being actually, tremendously important in finding a way, and this is where language models, I think, actually do come back into their own, ways of harnessing AI to help qualitative researchers to come up with new and interesting interpretations, and to do stuff that qualitative research takes an awful long time to get a lot of this stuff done. I think language models can really help with that, so that we can actually then get a better understanding of what those numbers mean that are coming from the other models.
I just had a thought while you were talking there, Robert, which is that sometimes I think in a qualitative systematic review, the objective is theoretical integration, right? You have some various different qualitative studies which have identified key themes around the topic, and indeed help to illuminate spotlights on maybe different aspects of that topic. And to add to this rich understanding, you try to do a theoretical integration. And here I think really it is an area where ontology-based representations, coupled perhaps in the future with language technology as it evolves, can really have something quite cool to add.
Yeah, and Susan Mickey, I think, is on the call, and I won't ask her to answer to address this, but I just want to make a note before we all forget that this is going to be a very useful thing to put into the next HBCP applications because it is going to come up as an issue. So the future of HBCP will include qualitative. Good question. Right.
Excellent.
Next one is, are there any risks of using AI systems to help us identify evidence? Again, Jana, interesting
so there
question.
are certainly risks, and I think it's a really important topic at the moment as more and more AI gets deployed into aspects of our everyday life. So I won't imagine that I could comprehensively list what the risks were, but I'll just sort of illustratively mention two. So I think one risk is that if we rely on the AI to do this job, we may miss important evidence because AI doesn't work equally well for every area of the research, right? It may systematically work worse on certain areas of the research, like research coming from different parts of the world or research with certain population profiles and so on. So we may amplify existing biases through the use of AI tools, and we have to work to avoid that. Another risk is that the AI itself, sort of, if it's a learning system being continuously updated, it may be vulnerable to being messed with in some way, to being convinced or trained or somehow injected with malicious or wrong content. And this just illustrates kind of two of the possible risks. I think we're living in an era where there are many risks being opened up in this area. Robert, what do you think?
So many, and I think I would just add one. Those are two really good ones. I would just add one, and that is the extent to which people come to rely on AI and forget that the human intelligence. And so, ML and AI can make ridiculous mistakes because they don't know anything. All they know is what they've been taught, and they're algorithmic. So the early AI chess programs, for example, would sometimes sacrifice their queen for no purpose because it looked like the right thing to do. Yeah, I think that the added risk is that we come to rely on systems that ultimately shouldn't be 100% relied on. And this is why the next phase of this project, which I hope we are able to get funding to do, is a human AI hybrid system in which you get the best of all worlds. So another good question. Next one is, so if this system is successful, there'll be no need for a systematic review or meta-analysis studies in the future, right? Wrong. Jana, tell us why.
Oh, I was going to say right. So I think there's a good case to be made for the idea that evidence that comes up new should be automatically integrated at the moment of publication with all the previous evidence. So this should sort of be part of the plumbing of the scientific ecosystem, and it should happen automatically. Does that mean it's not happening? No, that means that it is happening, but it's happening so frequently you don't have to do it as an action. So what do you...
Why do I think it's right? No, well, I completely agree with that. So the current sort of approach, of doing a meta-analysis, taking months to do it, or a systematic review, which takes months or years, usually is out of date by the time you've done it, and is very, very partial and only answers one of a squillion questions that you actually want answered in the data. Yeah, I think that's gone, or will go. I'm sure of it. However, essentially it'll be replaced by just imagine, this Brave New World where you've got the answers to specific questions at your fingertips, whoever you are, as a policymaker, as a researcher, whatever. It's all there in the system, and all you have to do is find it, and it will be there. It'll come to you. But having said that, I've been convinced by people who have argued to me of the importance of narrative. in science and telling a story. And so what I could see happening is that we get papers that essentially take the output from interesting questions that you can get the answers to really quickly and say, look what I found, look what I asked. It's a bit like, GPT, you've asked it a whole series of really interesting questions. You put the answers to those questions in a story and you say, okay, this is a human sort of integration and interpretation of what the machine is putting out. Janet, what do you think? Does that?
So that's a really good point. I think it's something that's missed somehow in the sort of overview that we've given so far, which is that a systematic review starts with a question. And if you don't pose the question, you don't have, even, if you've got all the data from all the studies being put into some sort of construct, which is automatically kept up to date, you still have to pose the right question in order to find the answer to that. And of course, there are automated approaches to sort of trying to guess what the right question is. But here, I think the human will always have a really massive edge because this is data coming from our world and the AI is not in our world, right?
Great, thanks. Yeah, so next question, speaking of questions, is can or does your algorithm judge the study quality or risk of bias? And would it filter out studies that didn't include a consort flow diagram, for example? Again, these are such great questions. So Jana.
So I think there's the evaluation automatically of the study quality or risk of bias. We are using the robot reviewer tool. It's sort of built into the pipeline to tag the possible risk of bias given the study description automatically. And I think that's the state of the art as far as automation goes in the area of flagging up risk of bias. Now, in terms of filtering out studies that don't have a consort flow diagram, I think here, this is not the intention. So I think that's not necessarily a pure indicator of the quality of the study. If it's because sometimes there may be technical reasons, it's hard to get to the consort flow diagram, which just have to do with the journal technical platform and not directly with the quality of the study.
Absolutely. And I think that's where, again, you're not going to be able to take the human out of the loop completely in the future. But what you can do, if you can get 90%, 80%, 50%, 80%, 90%, 99%, and I mean, that's just a massive improvement. But the other thing I would say also is that I think this approach actually takes you way further in terms of quantitatively assessing bias rather than having to make judgments on what you think could be a risk of bias. To give you an example in the field of smoking cessation, for example, blinding or failure to blind, theoretically gives you a big risk of bias. However, if you've coded as we have, well, actually we haven't, but if we had coded in this case and could easily, the extent of blinding, who's blinded, the patients or the participants, the researchers, the statistician, imagine that information being in there. You can then look to see what difference it makes. And then you actually know. And as it happens, we do have a potential risk of bias feature coded, which is funding source. Has it been funded by a pharmaceutical company, for example? And as it turns out, that does make a difference to the outcome. So what you can do here is not just judge things on whether you think they're going to be risk of bias, but actually whether they actually are in practice leading to bias. So I think that could be a big step forward. We're getting through the questions really well. I want to leave 5 minutes at the end just to sort of sum things up and take you to the next webinars. But we've got plenty of time. So, what proportion of papers don't follow consort? Well, I wish James were here, but I don't know the answer to that. Jana, do you know?
I'm afraid I don't know either. And what I remember, unfortunately, because James is striking today, he's not here to answer that question directly. But what I remember him saying at some point was something like, the further back you go, the fewer papers follow the standard, and now it's getting more and more. So this is trajectory is really good, but I don't know the numbers.
That is for sure. And I think in the field of smoking cessation, which is our use case here for HBCP, the vast majority do follow consort and have consort diagrams. However, I have to say, certain papers, which shall be nameless, in certain rather prestigious journals, which shall be named, such as the New England Journal of Medicine, have not put consort diagrams in, at least not in the paper, that they've shoveled them away in sort of supplementary material. So one of the things that we face, and this actually is a big issue for us in the field of behavioral science, is where, for example, intervention descriptions, as well as a lot of the details that you need to code, are not in the main paper. They're in a supplementary file or not there at all. And that obviously limits what you can do. Now, we can do better. We can get supplementary files into the system as well. We don't at the moment, but and Marijn de Bruin, who's done some fantastic work looking at what information about interventions in smoking cessation is included in the paper versus you have to sort of dig around or write to the authors to get, has shown that not only is only a minority of the information about interventions included in the paper itself, but it's biased. More information is included, if I've got this right, I remember rightly, about the intervention condition than control conditions. So control conditions are particularly badly reported, which of course makes life very difficult for automated systems. However, that will improve. And I think parts of this, what the HBCP can do, is to make sure that in future, or to encourage journals to make sure that in future information's there. So Abby has said, this is an interesting point. Does it currently only pick up English language papers? And if not, are there issues with translating the concepts? Great question.
Great question. Really, really important point. I think the literature base that we're looking at, which is this collection in the Open ALEX system, does include global literature, but our ontology so far is only available in English, and translation of ontologies is, as you can imagine, challenging because sometimes there are no exact or easy translations, but this work is work that we do plan to do at some point to a large extent. Of course, you cannot have every language in the world, but depending on prioritization and working with interested groups and partners.
Yeah, and in relation to the issue of translating the concepts, that is very important, but it's more important actually for things like mechanisms of action, the sort of not directly observable or things that you have to rely on, self-report, for example. So I remember that in smoking, for example, French doesn't really have the same concept of craving that we have in the English language, and in Polish, irritability, which is a nicotine withdrawal symptom, doesn't have a direct translation either, and we're going to have to deal with that. That is an issue that I hope, I know, I'm confident that we can, and actually ontologies provide a potentially way of doing it through semantic links and associations. So.
Yeah, they sort of are set up to handle that. So one thing is that you don't have to have a direct translation. You can have a sort of a broader or a narrower association rather than an exact mapping if it doesn't work. And the other thing is that your definition allows you to be quite verbose. You don't have to have a translation which is just label to label, if that makes sense. But I wanted to mention one other point, which is that translating or integrating research across different regions can be challenging, even if they're all in the English language, right? Because you can have some entities which mean different things in different parts of the world, even if they're all in English language. So this is a challenge which we're very aware of. It relates to sort of global integration and translation, given that people have different settings that they conduct research in.
I'm reminded of this in relation to US English and English, where the word quite in the US means very, which when someone is reviewing your grant application and they say it's quite interesting to English to English panel of grant awarding people, that's kind of not very helpful. So if any of you are American on this call, then please don't use quite, use very when you want to say how fantastic something is. So on that basis, thank you very much for the questions. We will get round to the other ones after the session, so don't worry about that. But thank you all for your questions, which are absolutely brilliant. And I'll just finish up now with the final comments. So here's a QR code which I'm going to leave up on the screen for as long as I can so that you can photograph it with your iPhones or your Android phones. If you've got any further questions, just click on, go onto the QR code, or click on the link that's actually posted in the chat box. So hopefully, even if you haven't managed to get your cameras out in time, you'll be able to look at the link in the chat box. But in any case, the chat will be sent to you. Okay, so what's next? Well, the next one in the series, March the 23rd, and this is going to be absolutely brilliant, if I may say so myself, and not because I'm in it, but because it's a conversation on what drove the HBCP in the first place. And Susan, Mickey, Jana, Christine Hunter, and our dear friend and colleague Mike Kelly, who was the head of public health at NICE, are going to be talking about these issues, and you'll have plenty of opportunity there to stick your two pennyworth in and ask questions as well. So that's something to look forward to. And I think last but not least, we're keen to get anyone who's interested to contribute to this brand new thing, which is part of the HBCP, but is going to be absolutely mega, and that's the behavior change technique ontology. Many of you will be familiar with the behavior change technique taxonomy V1, which is now incredibly widely used. Well, BCTO is its successor, and it's almost complete. In fact, it is just about complete. And what we're looking at for are people who are used to using BCTs, to examples of BCTs to try out the ontology with. So if you are interested, then do please get your cameras out, take a photograph of the QR code or link to the URL in the chat, and it'd be fantastic. And I know many of you will be interested to do that, and we'd love to have your input to it. So that's that, and then just this slide just shows where to get more information. Again, the slides will be available, so that's the first place to go, and they'll be on the Open Science Framework. The link is there, and we will send you details as well, so that you can find the information that you need. And I think that's about it. We're dead on time, so that's thank you all so much for attending. Great to have you on board, and I look forward to seeing you at the next webinar. So thanks, Jana, and thanks to you for attending, and thanks to the back room boys and girls for making this work properly. Thank you. Cheers.
Thanks
Bye,
so much, everyone. Bye.